right, so my name is Jason Clark. I work for New Relic on the Ruby agent team. If any of you have ever used the New Relic _RPM gem, that's the piece of code that I work on to maintain. So let's talk a little bit about threads and talk about what we're going to do with them today. So this is not a talk that's purely about concurrency. This isn't a talk about JRuby and Rubinius and why we care about concurrency and why the GIL makes life hard. It's not a talk about how you write concurrent programs. What it is about is it's going to be about how we can use the thread APIs that are present in the Ruby standard library to get some extra insight into what our applications are doing. The interesting bit about this is that even if your application is not multi-threaded, you can still get value out of these techniques. You don't have to be spawning a bunch of threads to be able to get some value out of this. So where are we going to go today? We're going to talk a little bit about how you profile an application. There's a couple of different major approaches that you can take to getting data, and we'll talk a little bit about the pros and cons of each of those. Then we're going to look at some code and build a simple profile ourselves here. And then we will look at how we present that data, because presenting the data and getting meaningful information out of it actually ends up being one of the harder parts of this problem. And then we'll talk about a few gotchas that come with the technique that we'll demonstrate. So let's talk about how we profile. There are two major ways that we can go about profiling an application. The first of them is instrumenting the application. So this would be an approach where we would use something like setTraceFunc or RubyProf, and we would wrap basically every method call that gets made in Ruby, and we get an exact duration on how long that took. This is awesome. It gives us all sorts of information and timings about what's going on, gives us all of the details that we want. And so this is just a great way to get a complete picture of what your application is doing. So why don't we just run out and do this? Let's just instrument everything so we can get all of the data about what's going on in our application. Well, not so fast. RubyProf, on their page, to their credit, they have put significant effort into making this fast, optimizing it. So it only makes your app twice as slow when you're running this. This is clearly something that's an awesome tool for development, and this approach is great for that, but this is not something that you're going to be able to run in production or in any sort of place where you're taking a significant amount of traffic. So maybe there's another way. Maybe we could just instrument some things some of the time. This is actually an approach that can work in production. If we imagine that we have some sort of stack, typical web stack here, and the colored boxes for the red and the blue kind of represent a couple of the most important methods that we're talking about. How about we just wrap those in some sort of timing so that we can get that information? Well, working for New Relic, obviously, this is something that we do in practice. This is how we take some of the transaction traces and things that give you these nice graphs of what goes on in your app. But I've highlighted the line there that kind of shows when this can fall down. Application code. Well, what's that mean? What's happening within that application code block? Well, if we can't instrument it, if we haven't chosen that as one of the methods that we're going to dig deeper on and put our hooks into, we can't really give you more information about what's going on when that's happening. So this is what pushes us to take a totally different tact as well in how we profile our applications. So instead of instrumenting, we can do something called sampling. So to give an example of how this sort of sampling would work, here's the same sort of stack that we have. For the purpose of the next couple of slides, I've boiled it down to some icons that'll be there. So if we imagine that we are looking at our application and time flows to the right, we take a peek at what's happening in our system at one moment. And we see that we are currently all the way down in our SQL. We're executing some sort of database query. Pretty common thing for us to be doing. We let a little time pass, and then we query again. And this time we find that we're actually in our Rails controller. That's where we're executing our logic. We're doing something there. Let a little bit more time pass. We take another snapshot of what's happening, and we find that we're all the way down in the database again. And then, we let another tick go, and we peek again, and we're all the way down at the database. So what does this picture give us? This doesn't tell us how long each of those calls took. This doesn't tell us how long it took for our queries to run, how long our controllers took. But what it does give us is a statistical picture over time of how often we are in each of those different methods. And if we run this for a long enough period of time, we can build up a picture of what our app is doing without having to instrument every single one of those methods to get the timing. Now, it gives us part of the information that instrumenting does. It doesn't give us all those great times, but we can get a picture of things that we can't viably instrument in a production system. All right, so what we're going to take a look at is building a sampling profiler based on this. So let's take a look at the pieces that go into making that. Everything that you need to be able to build this comes out of the Thread class, which is in the core of Ruby. And most of this is something that you might have noticed before, but there may be one or two of the pieces that you might not have been aware of. The first one is the easy part. So spawning a new thread is as simple as calling thread.new and providing it with a block of code. That block then gets handed off to a thread that runs asynchronously. In this case, this will just loop forever. Not particularly useful, but it shows how you get that code running. This is going to be a critical part of building our sampling profiler because we are not going to get called by the application. The application that we're wanting to profile isn't going to tell us, hey, why don't you go check things out? So we need a separate thread of execution that we can run on so that we can do our sampling at a certain interval. Once we've gotten into that loop, we can take a look at the threads that are there in our process. So thread.list will return us a collection of these thread objects and gives us a little bit of information about their state. So we can introspect everything that's going on. Now, what comes out of this list is going to vary dramatically based on your application. If you're running WebRec or something like that, locally, you may have 3 threads. If you're running Puma under JRuby, I've heard cases where people are running hundreds of threads concurrently that show up in this list. But whatever is happening in the process, you're going to get a snapshot of what's happening there with those threads. And then the last piece of our puzzle is the backtrace method. So each of those thread objects exposes a method that will give us an array of strings that represents where in the code it's currently located. So this is kind of a simplified example that I'll be using throughout the paths I've shrunk a bit to fit on the slides. But this is what the backtrace looks like. It's just a collection of these formatted strings that tell us the file, the line number, and the method that we're currently executing in. This may look a little bit familiar. You may have seen it in another context. So when an application throws an exception in Rails or wherever, the exception also has a backtrace attached to it. It's the exact same format of the information, but we're getting it from all of the running threads rather than only in error cases where that's happening. So with those pieces from the thread class, we are ready. So let's go build a profiler. The beginning place for us is that we need to get our profiler started. So we have a start method. This would be within a profiler class. And it's pretty straightforward. What it does is it spawns off that separate thread, so we get to execute next to the application, and then runs for a while and takes those samples. So our thread gets us out. So we are running asynchronously. We're running next to all of the application code. Our loop, we ask whether we should keep running. This is something where how you want to do this could vary. You could run this type of profiler persistently and that could be a wall true and let it go forever. New Relic's product with it, we do it for 2 to 15 minutes to take kind of a snapshotted profile. And so that method would tell you whether you're finished or not. We also sleep for a certain interval. That's necessary so that this thread doesn't try to gobble up all the CPU. We don't want to be sampling all of the time that we possibly can. New Relic's thread profiler does it about 10 times a second, and doing that over the course of about 2 to 15 minutes can build up a pretty good picture of what your app is doing. And we'll take a little bit closer look at some of those numbers later on. Inside of that loop, we just take samples. So we run, we take a snapshot of what the list of threads is, and we'll take a peek into how that method works next. So this is the most complicated part of our profiler here. So when we take a sample, we'll enumerate the list of threads that are currently there in the process. We'll step through each of those. This next line here, we're checking whether the backtrace is nil. Now this is kind of looks like a little bit of a wart, but it's something that it's good to be aware of. In some cases, if a thread has died, so the thread has finished its execution, we may actually get called to do a sampling before the Ruby objects for it have completely gone away. When a thread is in a dead state, its backtrace is nil. It doesn't return as an empty array or something nice and tidy like that. So we have to be careful that we may be in a state where we're going to get nils in there. Once we have that list of backtraces, then we can step through each of the lines that are there in that array, and then we'll do something interesting with them. In this case, what we're going to do for the simplified model here is we're just going to count up how often we've seen each of the individual points in the code. So those backtraces, again, look like this. So each of those lines is what we're enumerating over in that array, and those lines will get passed into our count backtrace line method. So to track this information, like I said, what we're going to do is we're just going to keep a simple hash that's going to key off of each of those specific locations within the code. It comes from the file name, the line number, and the method that's there. Now, for this really simple case, I could have just used the straight line as we receive it as the key, but it actually was useful to bust that up into a little bit more interesting format for some of the presentation purposes and some of the other ways that you might want to collate this information. It's useful to have it as more than just a string out of the stack trace. To break that line up, we just use a very simple regex here, and for these purposes, we're just going to take the list of the captures that come out of the array there, and treat that as the key. So in the case of this particular line, the resulting key that we would come up with would have the app.rb, then line number 5, and then the call method that was happening there. When this goes into our hash, that's just going to be there as the key, that prior call that we had, and then we're going to have an incrementing count. So each time that we go through and do one of these sampling runs, we're going to increment that count. So with that, we've actually been able to gather all of the information that we need to be able to build some sort of presentation out of this. So let's take a look at a sample application and how that works out. So on the Ruby agent team, we use the term trample when somebody stomps on something that they shouldn't. So this could be, somebody walks over a value, a variable in a multi-threaded context, somebody stomps on your git commit. So I made a little application to track tramples. That's what the setup is here. So in this application, we have a tromp method on our controller. And this does some totally reasonable things to be doing in an application. It'll calculate some Fibonacci numbers for us, and it'll do a big n+1, just to give us a nice juicy target for the thread profiling to hook onto. Fib looks pretty much like you'd expect it to, and the n+1 also looks pretty much like you don't want to actually do in your application. Don't use this code. So when we run our profiler, we can get this sort of output. So you see the file, the method, and the line that we've come up with. This is basically that information that we had extracted from it. And so we run it for a little bit, and then we take a look, and it's kind of not exactly what we might have been expecting to find. Like, where's our actual code? Where's the stuff that we wrote? There's all this noise. The noise makes sense when you think about it. Every time we look at the thing to sample, the root of our web server is running. So all of those layers of Rails or whatever you're running is going to show up every time you look into that sample. And so we need to do a little bit of filtering to get this information in a more useful format. So we've got a little hide framework button here. This works with just some simple matching. And once we clear out some of those pieces, we get a little bit better picture. We're starting to see some of our controller actions come through, some of the code that we've actually written. But well, we still have a little bit of noise here at the top. This is the profiler. So the profiler is running in a thread itself, so it sees itself executing. And that may be a little bit of fun, but it's not something that's particularly useful to us. So we'll just hide that information. And we end up coming down to a pretty concise view of just the application code that we really care about. So this is a very simplified view of how that can be presented. And it does have some drawbacks. If the Fibonacci method, for instance, was being called for multiple controller actions. One of the drawbacks of this sort of simple list is that we don't see anything about where that comes from. There's another way of viewing this information. There's probably a number of different ways, but there's another major way of visualizing it that will get us past that, and that's a call tree. So this is an image from New Relic's thread profiler, and this shows you kind of a hierarchical view of where that code descends from. This is information that we can get out of those backtraces and build up from the way that we gathered it. So let's take a quick look. We're not going to see code, but walk through kind of the algorithm for how that would work for building a call tree. So again, to remind, this is the stack trace that we came in with, just our simplified model. So the stack traces start from the bottom. So our application is the first thing, and so we'll start from the bottom of the list and work our way up. We will create nodes that will be represented as the tree that kind of will grow over there on the left. So we come in, we look at this line, and we don't have a node that represents us in our collection yet. And so we will just create it, and we'll create it with a count of 1. We step to our next line, and this is our controller's index method. And so again, we find that we haven't seen that before, and so we'll append that in as a child of the app. Now, the parent-child relationship there is the thing that's going to let us build that tree in the view that we saw previously. And then finally, our find method is going to come in, and we have a very basic, fairly boring tree. So let's apply another stack trace. So this is similar. It calls into our model at the same sort of location, but our controller action is a different action. This will be the show that we do. So when we come into parsing our stack trace, we see that the lowest level is going to be the same location, same entry point for our app. So instead of creating a new node, we end up incrementing the count. We look to the next line. That's going to be the controller, and it looks a lot like that node, but the action is different. This is actually a unique location that we've captured in the code that we haven't seen before. And so what we'll do instead is we span off a different child out of the app, a different spot that we're going to be at. And then in this model as well, we don't share nodes between those various branches. The leaves don't share once they've separated. And so although we have the same model 300 find that we were calling from the other location, we will represent that as a distinct node in this tree. So from this, I think it should hopefully be pretty clear how we can get this sort of presentation with those percentages. Those counts and the parent-child relationship is represented directly in that tree that we were looking at. So what are the gotchas with this approach? One of the big gotchas is that this is statistical. This is something where we are sampling over a period of time, and how frequently we do that, what sort of traffic it's under, and the size of the tasks that you're trying to catch matters. If you had some sort of application where most of the work that you were interested in trying to capture only took a millisecond, you're going to have a hard time capturing that in your sampling loop. If you have things that are taking tens or hundreds of milliseconds, it becomes a lot more plausible that the sampling thread is going to get a chance to run and get that introspection. As well, if there's not a significant amount of traffic going to your application, you're just going to see the web server sitting there idling in a loop. You need to have some sort of varied traffic being applied to it for this to give you interesting information, because it's just based on the statistics of what we saw during that period of time. It's also a little bit prone to effects from the fact that this is multi-threaded. I've noticed that it seems as though I/O-based operations kind of show up a little more often than the strict timings for compute-based operations. And it sort of makes sense, because our sampling thread is more likely to get run while we're waiting for I/O from another part of the process than it is when something's got CPU pegged and is going to use up the full amount of time that it has before it lets things go. Another question that people might have about this sort of approach is the overhead to it. So that was a very interesting thing. We checked it out a lot with the feature when we shipped this with New Relic, and we actually added a metric in to check what the polling time was. So the polling time for each of those times when we take the snapshot and aggregate it into the data structure. And what we found over the past several months, this is across probably about 1,000 profiles, was that on average it took about 1.7 milliseconds for each of those samples. which is pretty good. I mean, that's something that you could consider, depending on your app, running in a production setting, especially for a short period of time to try and help diagnose problems. If you know that you have some action that's happening, or you know that you have something that you can't get visibility into, this will give you a chance to take a snapshot of what's really going on at the lowest level. There is additional overhead as well with this approach for just the memory for holding whatever data storage you're hanging on to. So that call tree or that hash, for New Relic's purposes, we hold on to it for the duration until the profiling period is done, and then it gets cleared out and sent up to the collector. If you were doing this more persistently across a long, long period of time, you might want to do something where you pruned it at certain levels and made sure that you didn't gather too many bits of data into there and consume too much memory. Another gotcha is that this is only available on 1.9. You can list the threads. You can obviously start new threads back on Ruby 1.8, but the backtrace method is not there. So you're pretty much dead-ended at that point. It is there on 1.9, so that's what you can get this sort of visibility. We also found that in testing, the 1.9.1 version of Ruby on MRI was a bit flaky about some of these backtrace methods. This has ended up not being a big issue for us because of the 7 versions of Ruby that we're currently supporting. This is actually just about the smallest, with 1.8.6 being, I think, the only one that has fewer people on it. So if you happen to be running 1.9.1, you might want to take some care with taking this sort of approach, but 1.9.2 and higher, it's worked out great for us. Yes, there's a reason that there's not very many of our users on it. So, the other odd bit that we ran into was JRuby. JRuby does an awesome job of providing real concurrency and running things in separate threads and buys you a lot of those sorts of parallel things that you want with threading. The backtraces that we found with them occasionally were coming out with some odd data, and occasionally were null. It looked as though some of the Java threads that the JRuby stuff behind the scenes was using were getting kind of adopted up into Ruby, and then we couldn't take backtraces on them. We filed issues with the JRuby team, and we're working with them on both of these, but again, if you try to do this yourself or look into some of these things, don't be too surprised if you see a few odd results in there. The code for the sample application that I wrote on this is available on GitHub, and I'm Jason R. Clark on Twitter and GitHub as well. Thank you.